Our project is responsible for the optimization study for offloading the Shearon spent nuclear fuel pool using transportable aging and disposable canisters.
We were tasked with examining the feasibility of using 3D printing techniques to manufacture the TAD canister and impact limiter on a full and prototype scale, along with analyzing signal transmission using two different printed metals. We were able to research and examine the feasibility of the 3D printing of the TAD canister, impact limiter, and dissimilar metal lid. In the United States, nuclear fuel is not recycled. The spent fuel is loaded into TAD canisters. TAD canisters are placed within a transportation cask with impact limiters attached to transport the fuel safely. At the end of the process, TAD canisters are placed in a long-term dry concrete storage cask.
Our team has conducted extensive materials testing research for this project, specifically researching the effects of additive manufacturing on material properties. Our project process consists of research, design, fabrication, and testing. In this section, you will find more detail about how the team went about completing them.
With the use of ANSYS, a simulated tensile test was performed on a dog bone sample of 5356 aluminum. The pull-to-failure method was implemented and the 0.2% offset method was used to determine the yield strength. Values are close to non-literature values and values obtained from ARC Specialty. The crash test was also performed on a 2x2 honeycomb block using the static structural module. Two rigid blocks are used to simulate the load cell and the fixed base plate. The honeycomb performed as expected and can be used to absorb impacts to the canister.
The dissimilar metal primary lid was designed with the ultrasonic additive manufacturing process kept in mind. The internal geometry of the lid is designed in such a way as to help with manufacturing restrictions and increasing radiation shielding. The two wire designs on the right were created to suit each sensor required to monitor the inside of the TAD cask. Each wire was simulated using ANSYS to show the wires working under normal electrical load conditions.
We utilized a failure mode and effects analysis document for all parts of this project to attempt to reduce our design risk. The FMEA has undergone many additions. We have each deliverable evaluated. This comprehensive document is helpful to assess the best way to go about printing each item in a full and prototype scale.
Ultrasonic additive manufacturing was determined to be the most appropriate method for the manufacture of the lid. The solid-state welding technology ensures that the wire and wire insulations are not damaged. Wire arc additive manufacturing was the preferred process for the fabrication of the impact limiter, canister, and the cask. This process utilizes a welding technique and can therefore be attached to a robotic arm.
We learned that 3D printing methods for large-scale industry purposes are still relatively new and can be extremely expensive. We also learned that certain 3D printing methods are incapable of printing certain combinations of materials. Focus groups are important for compiling information from relevant professionals. Lastly, when planning projects, more time needs to be given to contact manufacturers.
Listed in this section are a number of items that we believe the Phase 3 team should consider. These suggestions consist of goals that our team was not able to accomplish due to budget restraints and unforeseen equipment malfunctions.